S R for the citrate. We also introduce, what's commonly used as a redox cofactor, in this case it's not a redox reaction, is a bioinorganic cofactor called iron-sulfur cluster. Iron-sulfur clusters are, as their name implies, combinations of iron atoms and sulfurs. The sulfurs can be contributed either through sulfur atoms, free sulfur atoms, and sulfurs from cysteines, right, SHs. There are a number of different geometries of iron-sulfur clusters. It can be one iron, one sulfur, 2 and 2. This is 4 and 4, and those are the main ones, and there are a few others as well. Again, in this case, they work to be able to bind the citrate in position to properly transfer the OH where it needs to go, but it, in this case, it's not a redox reaction. When we see them again in electron transport chain, then we'll be looking at redox reactions. Aconitase is relatively close to equilibrium. So the transfer of citrate, or the isomerization of citrate to this compound called isocitrate to distinguish it. It is then, so again, what's the goal of this? Fully oxidizing carbons, right? So we need to get electrons off. We turn CX to CO2 bonds. Isocitrate dehydrogenase does both steps. It's an oxidative decarboxylation. It both converts the alcohol to a carbonyl, and by doing so, that substantially weakens that sort of branched carboxylate in order for it to be displaced as CO2. Because we have an alcohol being converted to a carbonyl in this reaction, right? NAD is involved. So sequentially, this occurs the NAD step to form the carbonyl, and then the presence of that carbonyl allows this to break. So the product of this is called alpha-ketoglutarate. And with this reaction, again, it's relatively close to equilibrium under standard conditions of minus 8.4, but it kind of offsets with aconitase. So these are CO2. They are from pH. So what we'll end up with is okay. That's good. So citrate. Alpha-ketoglutarate is then oxidatively decarboxylated to the 4-carbon analog called succinyl-CoA. And notice there's now a coenzyme A involved in this, so we're reforming a thioester. It's an oxidative decarboxylation, so that carboxylate is being converted to a thioester. Do you see a structural similarity in anything that we've written today? alpha ketoglutarate, which is CO2. So you end up with CoA. The structures look a little bit similar to what we did at the beginning of class. With pyruvate dehydrogenase. Functionally, it's an R group difference, right? Pyruvate has a hydrogen, where alpha ketoglutarate has a CH2 carboxyl. But the rest of the processes are the same. You start with that substrate, it loses oxidatively, loses a CO2, so it goes one carbon shorter, it ends up as a thioester. Acetyl-CoA on the bottom, it's called succinyl-CoA on the top, and NADH is generated each time. The outcomes are the same, the reactions are the same. Alpha ketoglutarate dehydrogenase has a E1 group that does the decarboxylation. It has the E2 group, it has lipoic acid that transfers the acyl group onto a CoA. It has an E3, which uses FAD to transfer the electrons to NADH. Structurally, they're the same as well. Similar, I didn't say exact same, but they have the E2 cores for alpha ketoglutarate dehydrogenase and the E1, E3 shells with the active sites. And the subunits are sequentially similar, evolutionarily similar as well. They're homologous. Because the only difference in their metabolic outcome is the structure of the substrate in the body, right? The chemistry for pyruvate can be the exact same chemistry for alpha ketoglutarate. And in the end, they have the same outcomes. They further oxidize the carbon compound and store the energy from that oxidation in a thioester intermediate. In this case, it's succinyl-CoA. So in the end, because they're using NAD to form a thioester, the NAD drives this, and we have a pretty favorable reaction. And, right, the two carbons that went in have been regenerated as CO2, so we use it as CO2s. Of course, we will continue this on Wednesday. Right, that gets us right to the first 4 reactions of the cycle. So the remainder of the reactions are about taking this and getting it back to that. All right. Here's my thing.